Hi, my name is Virgil Serbanuta. I work for Runtime Verification as a software engineer. And Runtime Verification is a company that tries to improve software quality in general. And the tool that I'm presenting today, Custer, is a tool that tries to do exactly that. So in my presentation, I'll first talk about the K framework, then about the multiverse semantics that we are developing, and then finally about this tool that does property verification. So first of all, let's start with what is K. So K is an operational semantics framework. This means that it allows us to write semantics that describe how programs should be executed. And to do that, one would specify the language that he wants to model or perhaps the system, like you could describe, let's say, JavaScript in the K framework, or perhaps Python or any other language, or of course WebAssembly. Or we could describe how a MultiversX node works as a system example. If you do that, then the K system will derive a bunch of tools from this specification. Now, K's logical foundation is matching logic. This is many sorted first-order formalism with really nice model theoretical properties. So both of the things that I just said are important. First of all, because K is an operational semantics framework, we can actually execute programs with these semantics. And because it's based on matching logic, we can prove mathematical properties about these programs. So here are some tools that can be derived from such a formal language definition. So we can derive interpreters, we can derive symbolic execution engines, and we can derive model checkers. And the good part about it is that usually this can be derived only once, and then they'll work for any semantics. Now, let's talk about the multiverse semantics that we developed. So first of all, this has two parts. We have a WebAssembly semantics, which allows us to execute WebAssembly code. But that is not enough to run a contract. So people can write contracts in multiple languages, but they say that they write them in Rust, and then this Rust code would be compiled to WebAssembly, and the MultiversX virtual machine would execute them. However, when trying to access, there is a machine state that contains, say, accounts with balances and storage and so on, and other things. And when trying to access this state, the user has to use VM hooks. These VM hooks are actually some functions which are not defined in JavaScript. And when the virtual machine reaches the execution of such a function, then it will stop. It will execute the function itself, and then it will restart WASM execution. So we had to implement a semantics for a multiverse node, which contains the machine state and also these hooks. We implemented 120 out of 200 hooks for now. And most of the unimplemented ones are about floating point operations or cryptographic functions. These are not hard to implement, but we implemented them as we needed for now. Also, for now, we run only single-sharded contracts. Out of the MX SDK RS repository, we can execute, say, 75 out of 86 of the basic features tests, and 20 out of 21 allocation tests. And also, we can execute several contracts, like, say, the crowdfunding ESDT one, the multisig one, and so on. OK. Alignment has been lost somehow. OK, so let's talk a bit about performance. As you can see here, For the first 2 rows, we have around 4 times overhead when running with our semantics, as opposed to running contracts the normal way. However, for the last 2 rows, the overhead is larger. Now, even with that large overhead, these times are really great for formal semantics. However, we plan to improve them by a lot. Next, let's talk about Custer, which is a tool that does property testing and verification for the MultiversX blockchain. Let's start with an example. This other contract, which has storage, the sum, and also has an init function which sets the sum to some initial value, and an add function which adds a value to that sum. So this is as simple as it gets. So our first option for testing that is to use a JSON scenario test, and let me try to show you one. So could we switch to the demo, please? Right. So a JSON test has several steps. This one, in this first step here, just sets up some accounts. The next step, it deploys the contract, passing 5 as an argument to the init function, and this will set the sum to 5, its initial value. Then it calls the add function once with 3. This makes the sum 8. And then it calls the add function again with 5 as an argument, and this sets the sum to 13. At the end, there is some sort of assertion which checks that the state is as expected, and it actually checks that the sum is 13 here. So could we switch back to the presentation, please? So these kind of tests are fairly good, but could we switch to the presentation again, please? OK. So these tests are fairly good for writing use case scenarios that simulate actions that the user might take. However, I find them writing this JSON test to be a bit tedious, and the result is not as readable as I would like it to be. And also, they are a bit rigid, and they're not that good for writing symbolic tests. And I'll explain a bit later exactly what this means. So our solution is to start by writing the scenario test in Rust. And this has a few benefits that we will see right now. So first of all, we use the same language as the tested code, and they get compiled to the same framework, which gives us a lot of flexibility and makes it easier to implement the symbolic test. Could we switch now back to the demo, please? Thank you. So our test starts in the same way. We start by setting up some accounts. Then we we call the init function, and passing, again, 5 as an argument to the init. We initialize the contract. Yes, of course. Sorry, I didn't know that this wasn't readable. Is it better now? OK, sorry about that. OK, so again, we deploy the contract, passing 5 to the init function. This init sum constant is actually 5. And then we have several test functions. This one does exactly what the previous JSON example did. It calls the add function, passing first 3 and then 5. And this makes the sum 13, and we have an assertion checking that the sum is indeed 13. Let us run this a bit. So we have to compile the 2 contracts. It works in the same way as compiling a normal contract. we also have to compile, both the normal contract and the test contract. Okay, and now the test contract. After this, we can finally use the Casmer tool to run the test. So this will start by first running, initializing the contract, running the init function. This is common for all tests, so it runs at the beginning. And then you will see that it will start running the several test endpoints. Of course, this test passes because yeah, we didn't do anything interesting yet. So could we switch back to the slides, please, again? Okay, whatever. So I'll just tell the story then. So to make this a bit more interesting, like right now we are testing just that if we add 3 and 5 to the initial sum, we get the right result. So this may be enough for such a simple contract, but even when adding numbers, it may not be enough because we may have overflow. Like we are using big integers right now, but so they don't overflow, but still in general that would be a concern. So in order to do something better, we can do property testing. So when doing property testing, we would start with an endpoint similar to this one. But instead of actually, we add 2 arguments to the test function. The init function would be the same, but we would add 2 arguments here, the 2 values that should be added. Then we would assume, well, here we can restrict the input range for those values. It's not needed here, strictly speaking, but I wanted to showcase this. And then we would call add for those 2 values. At the end, we would test that the sum is, the final sum is the 2 values added with the initial sum. So if we call this test with 3 and 5, we would get exactly the same test as before. However, we can do a bit more here. We can actually generate a lot of random input values and run this test for a much larger input range. So I'd like to mention something. Before I said that JSON tests are not that good for writing property tests. They're a bit rigid. So here we have to check that the sum is equal to an expression. We cannot just check a concrete value. And this expression can get very complicated at times. So in order to be able to write such a test in JSON, we would have to have full support for whatever expressions we want to write here. And yeah, this solution seemed somewhat better. Okay, with that being said, let me first run this test and see how this works. Again, we run it with the same Casmer tool. And yeah, initialization will be the same as before. But then we will see that it starts trying to run the test with various random values. We have 2 tests here, but I only showed you one of them. OK, so as expected, the test has passed. Let me show you a test that fails. It's the same test as before, except that, well, it's a simpler version. But at the end, I also added this assumption that the sum is less than 100. So if we run this, this should allow this test to mostly work in many cases, but not all of them. Let me run the tool again for this test and see what happens. So you will see that this test, probably the first values will pass the test, but at some point, yeah, it just happened. So it found a value which didn't pass the test. And now our framework is trying to minimize the input test, that is, it's trying to find the smallest number that it can, that still fails the test. This is 95, and yeah, we are close to it. Let's see. Yeah, okay, it just found that 95 as the smallest number, the smallest possible number which fails this test. Let's now see what happens if we change the tested function. Let's say that in the add function we test if the value is equal to this large number here. If it's equal, we don't update the sum. If it's not equal, we update the sum. This is supposed to represent a corner case in our program. This can be a bug or it can be a vulnerability that somebody may take advantage of. But yeah, this is also this covers a really small fraction of the input space. So then it will be really hard for random number generation to hit on exactly this number. I suppose that we could run it basically forever, and at some point it will hit this number, but yeah, let's see what happens. So yeah, it will run with various input arguments, and unless I'm really, really unlucky, yeah, all the tests pass. Okay, so, right. Could we switch back to the slides, please? Okay, so if we want to also catch this kind of corner cases, we have to do a property verification. And let me explain what that means. So first of all, we'll use the same test code and the same contract code as property tests, but we will be able to verify that we cover all possible input values. So, and we do that by actually doing a mathematical proof that our property holds for all input values. To do that, we use symbolic execution. This means that instead of starting to run our contract with some random values as input, we will use actual variables as input. This makes execution much more complicated. As an example, when we add our value to the sum, we are not able to get a value there to store in the sum. So we have to keep this expression unevaluated and continue somehow with that. Also, when we have to make a decision based on our input values, like say we have an if statement perhaps, we usually are not able to tell which if branch we should take, so both of them are plausible. So we actually examine what happens on both of these branches. Because of that, our execution will look like a tree. And in order to verify our property, we have to verify that it holds for each path in this tree. This is to do that for this tool, we actually check that each leaf of this tree is a successful execution. This is still under development, but I will be able to show you an example today. So let us look at a possible execution tree. This is a simplified version of the other test that I showed before. So we have, at the start, we initialize our contract. Sorry. At the start, we initialize our contract. Then we have an user assumption that the value is less than 100. If that's not the case, we have a branch. But if that's not the case, this is a branch in which we are not interested, so it will end successfully immediately. If the value is less than 100, then we add our value to the sum. We then check that whether the sum is equal to the initial value. If it's not, we end with failure. If it is, we end with success. So proving that our property holds will basically mean that we prove that this failure branch is impossible. We cannot take that branch. Okay, could we switch back to the demo, please? Right. So I will run the same customer tool as before, but this time I will use it to generate a mathematical statement that tells us that our property holds. It will take just a few moments, right? And then let me run our symbolic tool for this property. So this takes a bit more time usually than running the random input, the random value test. So I pre-computed most of the results, but we are still checking now which branches are feasible and which are not. And let's see how this works. This is for the magic number example, by the way. So our tool detected that our property does not hold, and it starts dumping various debug information, which should help us figure out why the property doesn't hold. The most useful part of this is the execution tree, which looks, let me see, it looks like this. So execution proceeds normally for a while, then we branch on whether the input value is the magic number or not. If it's not a magic number, we get a successful execution result. If it is the magic number, here we get a stuck branch. And that happens because we try to execute until we reach successful taste, but of course we don't reach it here. We have a failure. So yeah. Usually we have more branches than here. And by following these constraints on the branches, we can figure out exactly in which case our property does not hold. So that was it. Yeah, if you have questions, please ask. Okay. Then I guess that's it.